Hello and welcome to the Daily Space for today. Oh my goodness, I forgot the date already. For today, Tuesday, September 17th, 2019. I am your host, Dr. Pamela Gay, and I am here to put science in your brains. Today, I'm going to bring you a quick run through of the news, and as promised, the European Planetary Sciences Congress is flooding us with new planetary science information. In today's first story, to quote how Fraser Cain described it, spring is exploding out on Mars. In the image that I show you here, you can see a variety of sand dunes spreading across the plains on Mars. And these sand dunes are located in the Martian northern hemisphere. And Mars, just like the Earth, is tilted a bit over on its side. And this tilt means that it experiences seasons the same way we do, where as that pole tilts more and more towards the sun, the surface warms up and, spring bursts out. And here I mean it a bit more violently than your tulips bursting. On Mars, it gets so cold in winter that carbon dioxide will freeze out of the atmosphere. And just like here on Earth, carbon dioxide goes from frozen solid blocks to gas without a liquid stage in between. And there is a massive change in volume as that carbon dioxide goes from frozen to gas. And, it turns out these sand dunes on Mars, they collect ice during the winter. And when that ice, which is just beneath the surface, melts in the spring, it bursts out in what look like splotches of ink all along the bases of these sand dunes. So when we look at this image and we see what looks like hundreds of black ink splotches, those are all places where the ground exploded, revealing all sorts of darker material beneath the surface. So if you decide to go on a nice spring stroll across the surface of Mars, can I suggest you don't go hiking in the sand dunes, because the ground may literally explode out from beneath your feet. And this is just no. Just no. Just say no. As we move into the future, we're going to see more and more stories on Mars. And this is because right now there are a myriad of scientists all around the world working frantically to understand the most they can prior to the Mars 2020 rover and the Rosalind Franklin rover, both launching towards the Red Planet in 2020. Now, with these missions comes mission planning. And part of mission planning is figuring out where your little rovers are going to rove across the surface. And both the Rosalind Franklin rover and the Mars 2020 rover are set to rove in places where they just might be able to find traces of, past life on Mars. For the Rosalind Franklin rover, the area that it's landing is an area that we now have a new ability to understand thanks to digital technologies. This is Oxia Planum. This is a generally flat area that is cut through by an ancient riverbed that just may contain, traces of ancient life in the clay minerals that fill this region on the surface. Now, the two images that I'm showing here are various, 25 centimeter per pixel images of this surface that have been shaded and colored to create a, 3D way of looking at the surface that allows better mission planning and better science to be done. These images were constructed by taking two different images that were taken from slightly different perspectives of the same place. And by differencing these images, you can get a stereo kind of view. Now, the way they made this makes sense to our human eyeballs when we look at a single image. is to shade the contours with light and dark to make it appear as though these are highly shadowed or highly illuminated regions. And then they used color to indicate altitude above the nominal sea level on Mars. In this case, red indicates higher altitude and blue lower altitude. By combining these color maps and illumination maps, they've created, well, images that allow us to see the most subtle ripples of sand dunes and all of the various, well, scientifically interesting features and hazardous features in this area on the red planet. Now, this is just kind of cool, kind of interesting. We're still waiting for the majority of the science to come out of being able to do this kind of study. But to me, the most interesting part about this is the images they used are all available publicly. This means that you can go out, download these images, and use them to create your own 3D world. Now imagine creating your next role-playing game in a 3D model of Mars. We have the capabilities of doing this. And this is how we plan missions, using virtual terrains before the rover goes out and explores them for real. Now, Mars isn't the only interesting object in our solar system, and in today's news, we're just going to keep moving outwards across our solar system. Our next story takes us, well, to an amateur astronomer's images of Jupiter. In these images that were taken, well, right here on Earth from, well, an amateur astronomer's regular, everyday, purchased off the internet, probably telescope, we're able to catch a fireball on Jupiter. I'm trying to get this video to play. Come on, video. The video does not want to play. Oh, technology, you're killing me. You're killing me. Nope, not going to do it. Okay, so I'm going to go to the next image that shows a series of these. Amateur astronomer Ethan Chappell in Cibola, Texas, back in August was able to record a fireball on the atmosphere of Jupiter. This particular fireball, because it was imaged using video, we're able to see it expand outward and then fade away. And this kind of data can be used to actually calculate out how much energy was involved in that explosion. And working backwards from the energy, they can figure out how big, how massive was that object. And astronomers at the Florida Institute of Technology, and this is Raman Kumar Sankar and Saba Palante, they were able to determine that the overall energy output of this system is consistent with an object that is 12 to 16 meters in diameter and consisted of 450 tons of material that disintegrated 80 kilometers above the Jupiter's cloud tops. Now, this kind of mass in this small of an object indicates that this was a stony iron meteor that impacted Jupiter. Now, what I love about this research is I remember back in 1994 when Shoemaker-Levy 9, a shredded comet, collided with Jupiter. Back then, we were being told that this kind of an impact event was potentially a once in decades, once in probably hundreds of years events, that we needed to all show up and look up and enjoy this experience we'd never get again. Now, while it may be true that that's the only comet we're going to detect ahead of time before it plunges in multiple segments into Jupiter in my life, it turns out that whole part about Jupiter not getting hit very often was entirely wrong. In the past 10 years, we've detected 6 different objects colliding with Jupiter's atmosphere, and it's now thought that there's maybe as many as 20 or 60 different impacts every single year. Now, with this many impacts, yeah, there's a lot of opportunities for everyday amateur astronomers to be out there contributing to science. And this is the remarkable thing. Prior to 1994, we hadn't seen any impacts. And every year, more of these are getting detected. And it's not that Jupiter's getting hit more often. It's that more people can afford the technology to go look at Jupiter with their off-the-shelf telescope, with their ordered off-the-shelf digital detectors, and see this kind of an event. And so here's to cheap electronics making better science possible. I just kind of find this event cool. That's it. Nothing really scientifically amazing. It's cool that we can figure this stuff out. I just think it's really cool that you can be like in your driveway and see this kind of an impact event happen. Now, from Jupiter, we're going to jump one more world outward, and this is, of course, the planet Saturn and its magnificent set of surrounding rings. Now, these rings may be one of the most beautiful objects in our solar system. You can debate that. But I think it's safe to say they are definitely one of the more confusing things in our solar system. How did they form? Don't know. How long have they been there? Not entirely sure. How long will they stay? No idea. There are paper after paper regularly being published with different models that make various prognostications on what they think they know about the origins, start date, and final date of this particular world. And this week is one of those weeks when more of this paper comes out. So in a new paper published in Nature Astronomy and presented at the European Planetary Sciences Congress in Geneva, we find new results from the French Observatoire de la Quantité des Azures. And these results put forward a new way of looking at the age of the rings. Our most recent best guess came from data from the Cassini space mission. As Cassini plunged through the rings back in 2017, they took detailed images. And in looking at these images, astronomers noted that the objects that make up the rings are bright, shiny, pretty-looking blobs of ice. And in our solar system, just like on our own planet Earth, you can tell the age of a blob of ice by how shiny white it is. Here on Earth, if you look at the snow and it's beautiful and it's pristine and it's fluffy white, you know that it's fresh. If you look at it and it's kind of covered in a layer of soot and grime and gravel, you know it's been there for a while. Well, while it's not buses and cars and factories that pollute the snow and dust in our solar system, that pollution still happens. In this case, it's micrometeorites raining down on the surfaces. It's organic dusty particles that are making up the interplanetary dust in our solar system that gets collided with. All of these different things can, over time, darken icy surfaces. And so it was assumed when we saw this nice, fresh, glorious, bright material that Saturn's rings must only be a few 100 million years old. But the research coming to us from this French university points out that other instruments on Cassini found that there are order of 600 kilograms of silicate material raining on Saturn's surface every second. And that along with all of those silicate grains, there are also organic materials raining down on Saturn's surface. And they consider dynamical models that are capable of carrying all of this silica, all of this organics outward across the rings, flinging it out into the rest of the solar system and inwards towards Saturn, and keeping that ice and dust clean. And if it's possible that the rings have this kind of self-cleaning mechanism, the question then becomes, well, how old are the rings? And here they look at dynamics. And in general, when you first throw a blob of stuff into outer space, it's tightly compacted. And over time, through dynamical interactions, material will spread out. This is true when we look at shredded asteroids and the asteroid belts and the way the various asteroid families have spread out through the belts. It's true when we look at material, well, in forming star systems. Now, when you look at Saturn as a dynamical system, it's possible that, yeah, it formed spread out. You can do that, but it requires a lot of coincidences and a lot of special circumstances. But if you assume that it forms through some sort of a standard dump mass in, collision of objects, whatever, you instead get a dynamical age of, well, about 4 billion years old, which would make Saturn's rings similar in age to a lot of the other objects that have formed throughout our solar system. Now, the reason I say a bunch of objects is because our solar system formed over time. Collisions occurred over time. The material that makes up our Earth, it came from a mix of a proto-Earth object and an object that we named Theia because we could. And Theia was about the size of Mars, and the proto-Earth and Theia collided violently, creating our Earth and the Moon. And so our Earth and the Moon weren't what started here. They're what ended up here after this age of collisions. And it was during that period of violence that it looks like Saturn's rings could also have formed. So it isn't conclusive. This isn't definite. We don't know for certain when Saturn's rings formed. But this is at least an argument that can explain why they're shiny white and, well, what is their dynamical age? And if they've been able to sustain themselves for 4 billion years, we're probably good to go for a while, and we're going to get to continue seeing. And our future selves, our children, grandchildren, and many great-grandchildren will be able to continue observing Saturn's glorious rings of confusion. Okay, so not all stories today are coming to us from the European Planetary Science Conferences. There is still other science going on. And again, we are looking at small objects. These just happen to be small, extraordinarily dense objects. Our next story comes to us from the National Radio Astronomy Observatories and include observations of a neutron star called J0740 plus 6620. We kind of suck at giving things pretty names. That set of coordinates just tells us where on the sky this particular object is located. And this particular object is in a binary system that consists of a neutron star and a white dwarf. And I'm going to take a moment to step back and explain the physics of these two objects before I explain why this system is cool. So white dwarf stars form out of the remnants of stars kind of like our sun. In their last gasps at life, stars like our sun poof off their outer atmosphere, and these layers of material become planetary nebulae. And what's left behind is the core of the star, and it's extremely hot and it's extremely dense. And the only thing supporting it from collapse under the force of its own gravity is what's called electron degeneracy pressure. We literally have the electrons in these white dwarf stars going, wait, Pauli exclusion principle, I can't get closer, I can't be more compact than a certain amount. And it's this balance between gravity and electron degeneracy pressure that puts a limit on just how big a white dwarf can be. Above 1.4 solar masses, that electron pressure is no longer able to push back against gravity. And if an object more massive than that 1.44 solar masses collapses down, it's not going to become a white dwarf. It's going to keep collapsing as those electrons and protons come together, form neutrons, and form a significantly denser object called a neutron star. And just like white dwarfs are supported by electron degeneracy pressure, neutron stars are supported by neutron degeneracy pressure, where here it's the neutrons pushing out against gravity. And if you get too big, the neutron degeneracy pressure also fails. And this is how you get black holes. And it's thought that point where you transition from neutron degeneracy pressure working to becoming a black hole is somewhere around 2.16 solar masses. And the reason I phrase it as somewhere around is because observations with LIGO and Virgo gravitational wave detectors is showing us that the neutron star mergers they're seeing are peaking out around 2.17 solar masses. And this object, J0740 plus 6620, this object appears to be 2.17 solar masses. It appears to be as big as you can possibly get when you spin up one of these stars. It's what's called a millisecond pulsar. This means that it's rotating about 1,000 times, about 1,000 times a second. And as it rotates, it is sending bursts of radio light our way. Now, because this system is in a binary system, it's actually orbiting. And as it moves away from us, those pulses of light each have to travel a little bit further to get to us. And so we see its pulses is getting spread out in time. And as it moves towards us, each successive pulse has a smaller distance it has to travel. So we see those pulses get smooshed together in time. Well, by looking at these pulses and by looking at how long this orbit takes to complete, they're able to very accurately make this measurement. This is how we know this is a neutron star right at the edge of collapsing into being a black hole. Now, this knowledge doesn't change anything about how we understand the universe. We have just found a really cool neutron star with a white dwarf star co-orbiting. But it's cool because if we had the right ears, we could actually hear this changing in the pulses as these two objects orbit around each other. And that's just kind of awesome. So here's to cool science and finding the biggest possible neutron star. And here is to the fact that this biggest possible neutron star, I'm going to make sure I get the numbers correct on this one. It's located 4,600 light years away, and it's only 30 kilometers across. I can bike ride 30 kilometers, and I don't consider it a very big deal. I could bike ride the diameter of this neutron star. If it wasn't a neutron star, if I tried to actually do this, it would smush me into neutrons. But yeah, we observed this object. We measured its mass. We measured its size. And it's 4,600 light years away. This is just cool. This is the kind of thing those of us who are into technology and observational science really get excited about. And I'm going to end on this kind of exciting story because why not? So that rounds out our episode for today. And I would like to remind you that The Daily Space is brought to you by either me, Dr. Pamela Gay, or my co-host Annie Wilson, who will be here tomorrow bringing you an update on, well, all things space launch, landing, and rocket related. We are a production of the Planetary Science Institute, and we are produced by Susie Murph, who is the great cat herder of all things related to this show. And thanks to you, we're able to pay Susie and Annie a living wage. And so please allow us to keep doing that. And if you are able, consider, becoming one of our Patreons on patreon.com/CosmoQuestX, or consider a sub right here on twitch.tv. This is, after all, September, and your subs are discounted this month only. So help us reach our goal of 50 subs this month. Resubs count. And we're brought to you by you. The Planetary Science Institute is a 501c3 nonprofit, and this means your donations are tax deductible where the law allows. Okay, I think that's all the random wall of text I have to bring you today. So I am going to click over to looking at the news and also seeing who all I need to thank, because I think good things happened while that stream was being streamed. So I'm going to click on over to Streamlabs and say thank you once I get to the correct screen to a whole bunch of people. And I may even be able to wake up Eddie to come get some bits. So thank you, DJ Chopper 1 for the follow. Thank you, Ryan4509 for the follow. Thank you, Trekker Kev for the bits. Thank you, Kevlar for the bits. Thank you, Wayne Johnson for the bits. Thank you all. Come on. Did I drop one on the floor? He got distracted by a dropped bit. Hi. So this is Eddie. We give Cheerio bits to Eddie when you give us actual bits. So he is also very grateful for everything you have to give. Okay, so now to take a look at all your questions. I'm scrolling back up to the top, and Michael points out, exploding ground sounds really exciting. Yes, perhaps more exciting than I would like to experience in real life. So, something new just came in. Can't read it across the room. Thank you, Planetary Pan. Thank you so much for the bits. Come here, Eddie. Come here. Ow. Hi. Do you want this? You do. Such a good boy. He's like, yes, I will take those. I will take those. Okay, and Veronica Cure, thank you for the bits. Come here. Come here. That's a good boy. That's a good boy. Good boy. Such a good boy. Okay, I need to get a doggy cam over here. I think I'm finally starting to find a less technology fail-prone setup for my studio. And I just need a dog cam that looks right here at the dog who is laying at my feet in hopes of bits. Okay, so scrolling. So the map that I showed you of Mars wasn't quite a topographic map. I mean, it kind of was, but it also it used a different way of showing the slopes using digitally created shadows to make it more human readable than your average topographic map. Hexacosacoron asks, why couldn't we do that with Bennu? Because we didn't have the right data. Yeah, that's the truth to a lot of things. So speaking of Bennu, we have added back in several images to Bennu mappers that hadn't previously been actually marked. They're images where people looked at the image and went, no, I am not going to mark this, clicked image done, and submitted an unmarked image. So last night I ran software that flagged all of these images, and I'm getting all sorts of reports that the software doesn't want to actually give people the next image. While we were recording, in the back of my brain, I processed this, and I think what's happening is the software is used to there being consecutive images where when one image gets finished, it goes to the next image. Except because these aren't concurrent images or consecutive images rather, the software is a bit confused. I'm not entirely sure. I'm going to give it a good kick after the end of this episode, but I'm not entirely sure how to fix it. So I'm going to do the best I can and mostly just be confused. And my dog is moving my desk. Okay, let's see if I can stop my desk from rolling away while I stream. Okay, looking for more questions. Tom Van Scooter comments, Bennu looks like someone already blew it up. Yes, it does. This is true. So Arinster asks, why would we think that when we get bolids that often here on Earth? So Arinster is asking, about why would we think that Jupiter doesn't get hit very often. Well, it's not that we didn't think Jupiter didn't get hit very often. It's that we didn't think Jupiter got hit by big things very often. It's one thing to be able to see a flash of light in the sky from an object that hit the Earth and is blowing up 60 kilometers up or less, and being able to see the explosion of an object in the atmosphere of a planet that's hundreds of thousands of miles away. It's that added distance that we just didn't think there were enough big objects hitting Jupiter that we'd be able to see these kinds of interactions. And it turns out Jupiter, with all of its extra gravity, it pulls in the big stuff and gets hit on a regular basis. Yes, Guido, it is the solar system's vacuum cleaner. It's also the solar system's randomizer, because what it doesn't eat, it flings in new directions. So Veronica Cure asks, why don't we have telescopes monitoring the planets all the time? You know, I asked that same question this morning when I was reading that article. It seems like it would be really low-hanging fruit to organize networks of amateur astronomers and all of these robotic telescope systems to make sure Jupiter, Saturn, all of these worlds are monitored all of the time. And apparently no one has done that yet. So, yeah, things to think about and potentially see about, well, putting together some sort of a network someday in the future. I need to find out who would be interested in using the data, but it's definitely something that I think CosmoQuest can look into. Our instro uses a I Heart with Ocean Waves Saturn, which is excellent. Okay. Looking to see what else is in here for questions. Aliens have not been confirmed on Saturn. No, they have not. It is a self-cleaning world, as Larry puts it. Okay, scrolling, looking for more questions. I like how our instro is like, I'm calling it Zero, or J for short, in reference to the neutron star, with the ever so poetic name J0740 plus 6620. Okay, looking for more questions. Mythtown gifted 5 tier 1 subs to CosmoQuest's community. That is amazing. Thank you so much, Mythtown. Okay, Eddie, you get a whole lot of treats for this one. If I like scatter them on my desk, will you be super cute and eat them off the desk? You will. Okay, he's just going to casually eat off of my desk, creeping into my lap as he does so. That is amazing. Thank you, Mythtown. Thank you. Okay, everyone needs to now like use all these new emotes they have. Eddie, there's still Cheerios. Come on up. Come on up. There you go. He's like, oh, yeah, there are still Cheerios. I shall eat those. Thank you, Mythtown. Okay, Larry Weird asks, is this millisecond pulsar maybe a kilonova remnant? Can we tell? We can't tell. Yeah, can't tell. Sorry. Don't know. So Michael Mayer asks, if the neutron star spins fast, the pressure on the neutrons would be a function of latitude. Could it collapse along the polar axes but not around the equator? So this is where systems get super complex to look at dynamically, because what you'll have is it'll get foreshortened at the poles, and you'll get more material at the equators, and it's getting pushed out by that angular momentum. And so it's not that it's going to collapse at the poles. There'll actually be less material between the center and the rotational poles of the object, and more material along the equatorial region where it bulges outward. And the physics becomes more complicated because of the way it's spinning. And you're right, the pressure will be a function of where it is in that latitude. But the material conforms to the equal pressure shape, essentially. It finds a way to redistribute itself so that it doesn't collapse like that. I like our Instro's habit of using emotes to put wings on things. It just pleases me. Scrolling, looking for more questions. Hey, Migzar, I'm not sure I've seen your name in the chat before. Welcome. Oh, Veronica Cure gifted a tier 1 sub as well. Thank you, Veronica Cure. And get those emotes out, JB McCool. Enjoy your new emote goodness. Come on, up here. Oh, I know, I dropped some. So looking to see what else we have in here. Don't forget the gratuitous doggy video feed. You know, doggy video feeds are a thing. Looking to see. Thank you for the bits, Veronica. Binary Blaze points out we're 17.41% of the way there for the face reveal of favorite human. Essentially, if we hit a certain donation mark, favorite human's face gets revealed. Eddie is a pretty boy. And no, Stella and Malachi do not like the basement stairs. I don't know why Malachi doesn't like them other than they're dark and kind of scary, like all good basement stairs. Stella has a good reason to hate them. The first time that we had her and there was a tornado warning, I scooped her up and was walking down the stairs, and she did this standard puppy flail thing and ended up knocking me, and she went flying, and it was a bad experience for everyone involved. We were both fine, but we did reach the bottom of the stairs more rapidly than intended. So yeah, Eddie, he's a bit braver and knows, as is being pointed out, there's Cheerios involved in coming down the stairs. So Michael Mayer is saying, I would be happy to try and help find the problem in the Bennu software. That would be amazing. I would need to give you access to our GitHub repository, but I'm happy to do that. I will Discord with you at the end of this. It's our Laravel version that's currently having issues. So Larry is asking, is Bennu an example of slow accretion? Probably not. Bennu is likely an object or a combination of objects that got traumatized during an impact, shattered, and then gravitationally came back together, but it wasn't a slow process. Looking, so Larry asks, is that millisecond pulsar J a kilonova? Oh, that's a repeat of a question. Don't know. Can't tell. Sometimes you just can't get there from here with questions. Oh, Raven Lillian has French fries. I now want French fries. I may do that today. I think the Cardinals got a home run, which means that McDonald's has cheap fries. So Wayne Johnson points out, is anyone streaming Bennu mapping this evening? I don't know. It depends on how much of my to-do list I get through and how much of her to-do list Annie gets through and how much brain we have left at the end of the day. Thank you to the anonymous gifter who gifted a sub. Coffee KX, welcome, and get those emotes out. Come here, Eddie. Come here. Come here. I know you like this. Here, I'm going to move this closer to you. That didn't help. Eddie has decided he won't put his legs up on the piano bench I'm sitting on. He will only put them on my thigh. And he's a big boy. I don't know why I pointed that out. Looking for more questions. Yeah, DPI 209 is like new coder. Looking at you, Michael. DPI 209 joined us in the closed repository a couple of days ago to help out. Carne asada fries. Oh my goodness, that's one of my favorite foods, and I haven't found a good place to get it outside of Tucson. You guys know that I eat lunch right after I stream, and you just torture me. I have not found a good place to get poutine in my part of the United States, which is a very sad thing. Do not get poutine at Red Robin. Even if they say it is good, it is not good. Anyways. I'm going to bring a close to this episode of The Daily Space. If you ever miss us when we're live here on twitch.tv, you can catch every episode archived over on youtube.com/c/CosmoQuest. Now, you may be thinking to yourself, I'm never going to miss an episode live, and we love you for that thought. But we really need help to get our audience large enough that YouTube will let us enable certain features. And we're not there yet. If you can use every Gmail account you have to subscribe to us over on YouTube, it would really help us get all the features we need to do the best we can with YouTube. So please consider going over to YouTube, giving us a sub. It's completely free on YouTube. And maybe play some videos while you're there. Just leave it on in the background. Learn some science. Please. And ask others. That's actually one of the best ways you can help us out, is to ask other people to give us a follow, to tune in to us here on Twitch, to, well, support us by being in our audience. You never know whose life you're going to change by introducing them to science. So recommend us to a friend. That's all we've got today. So this has been The Daily Space. We come to you most Mondays through Fridays at 1 p.m. Eastern, 10 a.m. Pacific. That is 6 p.m. London time. We also come to you on Sundays with the Sunday Science Hour, brought to you by Annie Wilson. And we go live randomly with launches, landings, and everything in between, including occasional moments of writing software live online, hate mapping worlds like Bennu, and all sorts of other sciencey, technology-rich goodness. So give us a follow and find out whenever we go live. And that's really all I've got for today. I am going to raid someone. I don't know who. Let me see if I can figure that out. Who would you like me to raid? I saw a suggestion earlier. Oh, we already have a raid going. Thank you, Annie. So we are now going to raid Horizon Psi, and I will see you all tomorrow. Have a fabulous morning, evening, afternoon, wherever in the world you may be. Bye-bye.